It is possible to export analog waveform data by selecting the waveform on the graph and pressing the Export button. If we take a look with the text editor to the exported file, we can note that the first two rows are respectively the sampling rate and the number of samples. The representation of the exported values is double. If you select a digital line and press the Export button, it will be created a comma-separated value file where each column represents the sample of one digital channel. If we open the export file with the text editor, we note that the header represents the number of the digital channel, and the digital data columns are separated by a comma. You can manipulate the exported data with a third-party program like MATLAB, LabVIEW, Excel, and then import the data in the True-Arb application. Let's get into it with some examples. In Excel, we open the analog1 export file and we follow the text import wizard. Once the data have been imported inside the Excel sheet, we can easily change the value inside the cells. I'm going to save now the Excel sheet in a new file called Analog Waveform 1 Export Mod, and the type is text tab delimited. I import the file I've just created to check the data. We will open now in Excel the digital data using the same text import wizard. This time the data are comma separated, so check the option on the step 2. I change some values on the line 5 and on the line 2. This time the file must be saved as a comma delimited file. We can import the modified file, digital waveform export mod, and note that the line 5 and line 2 have been correctly changed. We can import the two files directly in the True-Arb application. To do that, open the waveform list, press the import button, select the analog waveform 1 export mode, and select analog as export type. Press OK, and the waveform will be imported in the waveform list. We repeat the procedure for the digital waveform, but we have to change the extension of the file from comma-separated value to text file. Press Open, and then select Digital as waveform type. Press OK, and the waveform will be imported. With the Load Waveform button, you can load the zip files previously saved or load waveforms from the True-Arb waveform list. If the waveform that you will select will be shorter or longer than the waveform in the editor, the software will give you some options. In this case, the waveform is made of 400 kilosamples, while the waveforms on the waveform editor are 100 kilosamples. So, in the software, we select Cut the tail of loaded waveform. The Cursors and Tools tab provide you a set of tools to identify and highlight waveform data. I would like to underline that the cursors are not physical markers, but they are just tools used to make measurements on the graph or to search for a particular value. Click on the Show Table button to display the cursors list. This list shows all the cursors present in the waveform editor window and their absolute and relative position to the master cursor. It is possible to add cursors, move them by clicking and dragging on them, you can set a master, or you can remove the cursor 3 with the Remove button. The search tools provide you several functions to identify a specific time event like a bus value, a signal value, a rising or falling edge event. Press the Setup button to open the Search Settings window. On the left, you have a tree control with all the signals that are present in the waveform editor, and depending on the selected item, you will have a different option in the compare and value fields. Let's search for 300 mV in the analog waveform 1. If you press the next or previous button, the software will find 300 mV values on the first analog waveform. The master cursor will position on the found value. We can find now a particular value on the digital data bus. We select Compare Equal, and on the value field we choose 3. Press OK, and when you press the next button, the software will find the specified value. In this last example, we are going to find all the rising edge events on the clock signal. Press the Go to Start button to go to the start of the waveform editor graph. Press Go to End to go to End, go to Sample to go to a particular sample number, and go to Cursor 0 to go to the Cursor 0 position. The graph tools give you a group of functionalities to manage the waveform graph area. The hand tool allows to drag the graph visualization area. The pointers allows to make an area selection, to move the cursors and to select the data in the table. Finally, with the graph property, you can change the properties of the display area like the background color, the major grid and minor grid color and visualization, and the signal spacing. There are some cases where it is not possible to create a waveform by using a combination of segments and components. The formula editor is a powerful tool that lets you creating advanced waveform using equations. Now I will introduce the formula editor by using some examples. Press the Edit Waveform button and select Formula on the drop-down list to open the formula edit. The equation can be based on samples x or time t. Let's type 10 multiplied x and select Preview. The software gives us an error because the amplitude constraints are not expected. So we change the formula in this way, press Preview, and now the formula is OK. We can do the same using the time, so 3 multiplied t, and check the formula with the Preview button. In the first example, we will create an exponential decaying sine waveform with the formula v multiplied exp of minus t divided by tc multiplied sine of 2p multiplied t multiplied f sample rate. The second formula is a rising exponential waveform, and it is based on 1 minus exp minus t divided by tc. The third example is based on an amplitude modulated sine waveform equation, that it is sine of 2 multiplied pi multiplied t multiplied the sampling rate multiplied 1 plus k multiplied cosine of 2 multiplied pi multiplied t multiplied fm. The final example is based on a Gaussian pulse waveform formula, where the formula is exp of minus 1 divided by 2 multiplied t minus tm divided by t sigma at the power of 2, where tm is the time location of the mean of the Gaussian pulse, and t sigma is the half-width point of Gaussian pulse that corresponds to the standard deviation sigma. I press the preview button, but this time I've got an error because there is a syntax error in the formula. We need to insert another bracket at the end. Press preview, and this time the Gaussian pulse is OK.